All right, guys, let's get started. It's 2 o'clock. Okay, so this is week 8, right? So just a few, pieces of information. No midterm, obviously, because we had exam 1 on week 6. The next exam will be on week 12, right? And we are on week 8. The exams are comprehensive, so anything from the beginning of the semester until that point in time. You've completed 2 homework assignments right now. You did the WECA homework, should be graded, I believe. And then the PyScript homework, I'm currently grading that. If you've demoed, I think I already gave you the grade. Yeah, so those are the 2. You're going to get a new homework assignment, homework 3. It's going to be about PyTorch, obviously, which is what we're covering right now. Remember that we've done a few algorithms from scratch. I'm still going to do the multi-layer perceptron at some point from scratch in NumPy, but my focus for the second third of the semester is PyTorch, right? To get, state-of-the-art program. So we started that, and today I'm just going to do a quick review of it. And my goal is just to get our very first set of PyTorch algorithms going with the Iris data set, okay? Remember that PyTorch, I've given you all the background, is pretty powerful, uses, you can use GPUs with it, and so on. So we'll be using Scholar, but I will do a demo also on another tool called Colab. Colab is a little bit more limited in the sense that you have to pay after a certain point, but it is free for a while. It's provided by Google. It does have its advantages. So it's still going to be in PyTorch. So I will do that demo coming up in the future. The homework assignment for the PyTorch one will be just, some data set, and I'll ask you to create some neural networks using PyTorch, okay? So I haven't decided yet what the homework will be exactly. It could be images or something like that. But I'll create that homework. But today, you're not ready for it until we finish these sets of algorithms. All right. Yeah, that's the plan for this week. All right, so let's go ahead and get started. Remember, so a few things. Your link, Machine Learning Foundations. This is where all the scripts live. I'm loading these on the 2025 folder. I haven't loaded the current one since we haven't finished it, but I will be loading it as soon as we finish. I did provide some reading materials that you're supposed to be reading. This is one of the most crucial things to read this semester, and I strongly recommend that you are reading it. So remember, so we've done all of this, machine learning, matrices, machine learning, WECA, KNN, perceptron, exam 1, Hopfield networks, and we are currently here, right? We are currently at the classic Iris torch to motivate NNs, all right? This is what I'll be building. I provided several links, but if you remember this one called topic notes, click on it again. Make sure you are reading this text, okay? Make it, it's got all the essential things in Torch to go from a very basic linear regression model all the way to deep learning, okay? To, a multi-layer perceptron, deep neural networks. It also talks about cross entropy and everything like that, which I will cover as a special, as a specific topic coming up. So you need to go through all of this material, binary cross entropy, all that. And I will do these both examples with Iris and with the wine data set. Those are essentially the critical things before week 12. And then after that, during the last third of the semester, we'll probably look at a CNN, and we'll look at something called transfer learning and a ResNet, okay? And that's essentially the whole semester. There may be a few algorithms in there like XGBoost and naive Bayes additionally to round out the semester, okay? But that's essentially what's all the material. But this document here, I provided the link for you. Make sure you read it and understand it correctly, because on the second exam, I will definitely assume you've read through this, okay? And so you need to make sure that you understand it. All right, so let's go ahead. So I'll close this link. Let's go back here. So I'm currently going through, you have several notes and several examples that we will cover. But essentially we are doing the iris example here. Just that. This one. Right, and this link, I'm literally doing this one, right? So this script classification DL iris is the example I'm currently doing in class. So you can get the notes from there. All right, so now let's go ahead and start our Jupyter notebook again. So I'm gonna do the kernel, restart and clear output. I've covered this already, so I'll just kind of quickly go through it. And then we're just gonna pick up where we left off, okay? So we're trying to build neural networks now for the iris data set, which is familiar to you. So you have 150 samples, right? 4 features in one class. This is a classification problem. We're going to split it into 80% for training, 20% for testing, all the usual stuff, right? And I'm just showing you really how to do PyTorch with this. And then later we're going to drill down into the theory of how things work. Okay, so let's go ahead and hit run. Okay, I'm going to load the libraries. So the key one, Torch, which allows you to build deep neural networks. All right, you can see the bullet is thinking there. All right, there we go. And then we have a few other libraries like model selection, train, test, split from zsklearn. We're going to continue to use that. And we're going to continue to use our metrics for classification. All right, there we are. Then I have a few variables such as batch size, learning rate, number of epochs. We've discussed what these are. As I said, the beauty of this thing is we did perceptron. Maybe everything was like alien, but now we're doing things with PyTorch, and 40%, 50% of what we did on the perceptron we're still doing. And as we continue advancing, by the time we get to deep learning, 85% of everything is the same. You see what I'm saying? So that's the real nice thing about this, but just don't fall behind. All right, so we got the batch size, the learning rate, the number of epochs. All right, so we run through that. We load the iris data set, which you already know, with pandas. And I'm also going to print it out as a pandas data frame. You can see that there. Remember that the key thing is that pandas, I like, some of this is my own preference sometimes. I like reading data into pandas, playing with it in pandas at the pandas level. Then you convert it to NumPy and then to PyTorch at PyTorch tensor. So here I have 150 rows and the columns. I performed this map to convert the words of the classes Setosa, Virginica, Versicolor into numbers. And I do that at the pandas level. So that's the nice thing about this is that since we're doing it at the pandas level, it's easier to do, okay? We can look at this is just to print the correlation matrix, gives you some insight, just like we did if you guys remember feature ranking in Weka, you can still do feature ranking here, but we also use this correlation matrix just to get a feel for the variables, okay? So I'm just going to go ahead and do that one. And you can see here, this gives you an intuition of what variables are related to what, and so on. So that's an approach. Then I take the pandas data frame and I'm going to convert it into a NumPy array. So you can see that here. And it's just a NumPy array. So all of this should be familiar to you as we've already discussed it. And that's kind of why I'm going at this pace. If you have any question, let me know. Okay. Excuse me. As you can see, once again, data slicing. That's why it was so critical that you at the beginning of the semester did those 70 to 100 tensor operations. You can see that that never goes away. And in fact, as the algorithms get more complex, we get a few more operations going. This allows you to slice the X data and the Y data. So here we have some of the Y data. And then here we see the data type is int. We set it as int. And that's because the classes can be int. All right. Now, one thing that I recommend that you always do, that it was done in Weka, and that I like to do, is print the histogram of the classes and the number of samples per class, because that just tells me how hard the problem will be, right? I have a data set called for fraud detection, and I may assign that as a homework because think of a bank, right? In a bank, hopefully 99% of the transactions are not fraud, right? If you have a bank where half of them are fraud, you have a serious problem, right? So you really don't want that situation. And so, but that's a very challenging machine learning problem when you're dealing with class imbalance. So, I may give you that as a homework assignment for you to play with. I believe the data set is large also, so that presents some good challenges. So we know that we have 3 classes. I'm going to print the histogram over here. You guys know from this histogram that the data set is balanced. Knowing that the data set is balanced is good. Okay, we do this. You can see I've split the data into 150 by 4 and 150 by 1. We talked about the randomness of things, right? That was one of the last things we discussed the last time around. And we said that randomness is good. As you run this Jupyter, you want to randomize the data always. So that just allows the model to kind of look at the data in different ways, right? So it's kind of like if I just always looked at this class like this, I would say everyone wears a blue shirt. And I never kind of look over there where people are wearing red shirts. You know what I mean? It's kind of like that. So you want to randomize things so that sometimes some of the red wearing people are over here and I see, oh, no. So it's kind of that intuition. All right, so we did the randomness also. And then you're familiar, train test split. If you can put your data in X and Y, it always fits in your code. So you can almost think of this as a template. All right, so we go ahead and do this one over here. And then now I have my shapes, 120 by 4, 30 by 4, 120 by 1, 30 by 1. The data type, I talked about this, really important nowadays, especially, where the algorithms are getting more advanced than the computing power we have. And so we have to start finding efficiencies, such as serializing, making the variables smaller, right? So currently these variables were float 64 for the X data, float 64, and that takes up more memory and more space in memory. So we convert them to float 32, and that gives us an efficiency. Does that make sense? And there you are. I believe this is the last where we were on the last time we met. And then the last part, we were almost ready to convert our data from NumPy to Torch. Remember that NumPy matrices or tensors are not going to connect to the PyTorch computational graph, and it's going to give you an error, essentially. All right, so go ahead. The data is the same, but the data structure will not work. All right, so we're done with this. So now I'm going to go ahead, go back to my, show you where I'm getting the code, right? So go back to my table of contents here. So Perceptron, Hopfield Network. So we're the classic Iris torch. So repo torch, right? So you can click on that one over here. And I'm doing my classification. So just using this code and and just describing it. All right, so this is all that I've copied from this already. All right, so we just did, that, right? So I just converted the tensors into torch. The next step I'm going to do is I'm going to normalize the data. So with Iris, the data is almost normalized in the sense. We've talked about this concept before, right? Let's say, for instance, you have one variable that is, from 0 to 100,000, and then you have another variable that is from 0 to 5. Those two axes, right, in the vector space, one is going to be very large, the other one is very small, right? And it's the larger values, the larger differences are going to dominate. You don't want that. So instead, what you do is you normalize all data to be within the same range. Let's say from 0 to 1. Make sense? That's called normalization. There's essentially two types of normalization, which are, although the term I'm using here is normalization, there's normalization and standardization. All right. I usually use standardization. That's just my preference. It's just, but you can use normalization as well. Standardization essentially makes everything be centered at 0, all the values, and then -1 and +1, whereas normalization just makes all values in the range from 0 to 1. But the point is they're all consistent in the same range, and it's just an equation. You can use a library, but it's essentially very straightforward, okay? So I'm going to show you today kind of how to do that. So let's go ahead and do standardization. So I'm going to go to Jupyter Notebook. All right, standardization, cell type, markdown, standardization. All right. And I'm going to all right. So as you can see, now you can normalize or standardize both the X and the Y data. For some specific tasks, you can do that. But especially if it's a regression type of a task, with multiple outputs. But in this case, we have the classes, which are, for Iris 0, 1, 2 integers. So essentially for those, you don't need to normalize it. The classes in this context do not need to be normalized, but the X data, the 4 features like sepal length, sepal width, petal width, do need to be normalized. All right, and so that's what we're going to do here. So for each column, we're just going to find the average, the mean of all those values. You guys see that? So, I have each sample of 4, and I have a sepal length that is 2, then another one that is 3, then another one is 2.1, another one is 3.7. I just want to find the mean for each of those columns. That's essentially what I'm going to do. So I'm going to not perform this for the Ys, and instead just perform this for the X's. My recommendation in machine learning is you always want to standardize or normalize your X data. It's like, if you haven't done it and you get a certain set of results, you may get much better results if you do it. So it's always something that I would highly recommend. So you have X-trained neural networks like it for some reason. It's a very important component. All right, so if you notice, I'm going to take X-train because this is a torch tensor. Now have built-in methods such as mean and standard deviation. Notice that you just specify the dimension that you want. So when you say 0, it would be the mean across the columns. If you set 1, it would be the mean across the rows. So what makes sense here is to take the mean across the columns, right? So four columns, so 4 means, all right? So that's what I'm going to do here. You can see that epsilon was in there just in case a value, because you're going to divide by this value, so you want to make sure that it's not a divide by 0 issue later on. So we take from X, the mean and the standard deviation, and we just save it in these 2 variables, okay? So I'm going to go ahead and do that, all right? So that's done. And then we can print it out if we'd like, just to take a peek. So you can see here, when I print X means, I have 4 values. So that's essentially telling me that out of the 120 samples, those are the means for feature 1, then the mean for feature 2, then the mean for feature 3, and the mean for feature 4. All right, so that's the example. With that information, I'm going to calculate or standardize the data. So now I do x means dot shape. I'm going to hit run, and that gives me that it's a vector 1/4. As you know, I like to look at the shapes constantly to get a feel for how the neural network is behaving. All right, you do the same with deviations. And you can see there are also 4 values in here, which are essentially the 4 standard deviations for each column, just like you learn in your statistics course. All right, then we proceed over here. Same thing with the shape. Print it out. 1/4, right? So the dimensions are important as we are going to perform some operations. Then we are going to, you can standardize the data if you'd like. So we'll take a look at that in a second. This would be let me look at the wine. All right, so it should be something like so it would be this scaled now equal that, right? And then this should be minus x means divided by standard deviation. Let's take a look at this one. Okay, so that worked just fine. Then I'm going to do that. I'm going to print the shape. So you can see the data is still 120/4 because it's still the same X data. But now let's take a view at it. Right, and you can see that the values are in a different scale. So if I do the original one, X train TR, do you guys see that? So the values are 5, 3.5, 1.4, 0.30. Does this make sense, guys? But after you do the standardization or scaling, they do look as if they are different, right? So, and this is essentially neural networks like this, for the data across the layers, actually, etc. Okay. For Iris, this is not such a crucial step, but it becomes a very crucial step, definitely for more complicated problems. All right. The next step seems to be the data loader. So this is actually pretty critical. My recommendation is the following. Students see something and then they don't get it. And then they go online and they try to implement something they find. And then chaos happens after that. My suggestion is learn this data loader well. Understand what's going on, because this is the best way to wrap your data and then feed it to a neural network, right? It'll, you know, that little bit of time that you take to understand how these things work is going to pay off later when you don't have to write 30 additional lines of code, okay? Because it does it for you. So let's just go ahead and think of how this looks. So we know it's the classic CSV file, right? Samples, you have the columns, right, for features, and then you have the columns for the labels. All right, so let's take a look over here. All right, so create a data loader. So again, let's print out the shapes just to get a feel for it. So I'm going to do X-train shape 0. You know, that tells me there's 120 samples. Okay. So now I'm going to create the thing that you have to create is this. This is like the crucial part. So as you can see here, I'm doing 2 list comprehensions. One is for Iris train list and one is for Iris test list, right? So if you notice, train and test. So this is a list of tuples, okay? That's essentially what it is. You create a Python list made up of tuples that are the tensors themselves. And so as long as you always do this, right, you will all and are able to create these 2 lists, then you will easily be able to use these 2 lists to initialize your data loaders and data sets. All right, so let's take a look at how this works. So you do, in the list comprehension here, you're going to do for I in range, and where the range is this, X-train shape. So that just means, I just printed this out over here. It just means that you have 120 samples. So every single one of the 20 samples now is going to be added into this list in this format, which is a tuple. All right, so if you notice, you're going to use I as an index. So then from X-train TR, you grab I, which essentially just means you're grabbing that row as is. That vector of 4 gets plugged into this space. And then from Y-train TR, you grab I, and you just say item so that it is not the tensor version of it, but just literally that integer that you want it to have. Does this make sense? And we can view these lists in a second, and then you do the same for the X test. So if you notice, for I in range X test of shape, right, this is going to be 30 most likely, right? And then you grab X test TRI, so that's the vector of 4, plug it into the tuple on the first position, and then Y test TR dot item, which plugs in the label itself. All right. If you have images, you'd have an image, let's say MNIST 28 by 28, spaghettify it. So then you would have what would be the size of this vector here for MNIST. If it's 28 by 28, 784. And then you just add the label. So right there, you know how to do images, you know how to do anything with this approach, and then you just give it to your data loader. Okay. All right. So let's go ahead and do that. That's a critical thing. If you know how to do this process well, it's going to save you a ton of time, because then everything just starts fitting with the rest of your neural network. Here, for instance, we can go ahead and print a few samples of this. So I'm going to grab from the train list that I just created, right? So I'm grabbing from this train list, and I'm going to do slicing once again. So from beginning, the first 3 I'm going to grab. So let's take a look at what happens. And as you can see, I provide from the list, you notice there are 3 tuples in here. This is the first tuple, which shows you that it's got a tensor of 5.1, 3.5, 1.4, 0.3. That's the first sample. And then it shows the actual label that is associated with it in the second part of the tuple, and it's just showing it as an integer. So this data structure, the tuple, literally looks like this, right? And so that's 2. Let's say I grab this sample over here. So that's just 2. And then here, this is not a list, but a torch tensor that has the values. Does that make sense? Very important that you understand this part. All right, so that's done. So now I've converted my data into the format, right? And what I want to do now is load it into a torch tensor. So if you look, since it's already in this format, I can just go ahead and instantiate my data loader. So I'm going to do this. So I'm going to create train DL. Remember, train DL, not test DL. And from torch.utils.data.data loader, I just need to provide my iris train list, which is this one, in the correct format. So this approach will get you really far, right? So it'll get you across, many tabular data sets, many image-based data sets, and so on, until we reach CNNs, which of course would have a different way of processing things. Now, one really nice thing about a data loader is that it provides internally several features. So one of them is, we don't, of course, here in this example, we could feed all 120 samples to the neural network at once. That's fine. But let's say that you start training on Sci-Far 10 and you have 70,000 images in color. Those become really big tensors, right? And the neural network becomes really big. So at that point, you can't just give 70,000 images to the neural network at once. Do you see that? That's not possible. So instead, you have to, this example of the coal in a train, right? So you shovel coal in a train, so, in batches, all right? And so that's what you do here. So you specify the batch size, and that's all you have to do. Then the algorithm will extract from the data batches for you to feed your neural network. But it handles all that code for you, which is really nice. The other part, shuffle equal true, is basically that every time that you start using that particular data loader with that data, if you specify shuffle equal true, all the data is going to be shuffled. So that's randomized, and you're not always feeding all the data in the same order. Every iteration, you feed the data in a different order, in a different order, in a different order. Okay? So here we have then torch utils data loader, iris train list, batch size, we shuffle, and we assign it to train DL. Okay? So that's essentially the first part. Any questions, guys? Does this make sense? If I can't stress, right? Before this, I would have spent a week or 2 extra just to teach you how to do all this manually. Now, if you take advantage of this, I mean, you can really quickly get going, okay? And it's way more efficient and better, just better in many ways. All right, so I've done that part. We can take a look, for instance. Well, I've done this already, X-test shapes and stuff. Oh, yeah. This is an important one. So notice what I'm going to do here, right, guys? Questions?
Oh, sorry.
Oh, yeah, no, it's recorded. So just watch the video. So for training, so this might happen sometimes, right? So for training, you're going to have lots of data. You might have let's say images, right? You have 60,000 images. So you have to feed in batches of 64, 32, whatever it is. It'll be one of those things that you have to figure out. As I said, hopefully maybe next week I'll start to show you how to use Colab. Scholar, we've been having problems this semester, but hopefully that'll get fixed. You have to kind of batches and GPUs go together, so you have to play with that. But for the test set, sometimes because you're not training, you don't really need to provide batches, and instead you just tell it that use all the data as the batch size. So you can see that's what's happening here. I'm grabbing from X test shape 0, which should be 30, because there are 30 samples, right? I'm assigning that to the variable all test data, And then in batch size here, I'm just saying 30. Okay, I could have hard coded that, but I just used a variable. And that's because I'm creating a new data loader for the test data. And here, I'm not going to read it in batches. I just grab all the data and give it to the model. This is going to be, this was a question on the exam, right? What's the difference between trained data and test data? So trained data, you do repeatedly to train the neural network. The test data, you only do once. So you don't need really, but you still need to specify a batch size. So in this example here, I'm going to just copy this. I did the train data already. Now I'm creating a test DL to evaluate my model. Torch.utils.data.data loader. Notice that I give it the list Iris test list. The batch size is going to be all test data, and I shuffle it as well. That's fine, because I'm only doing it once anyway. Excuse me. If you notice, I have now created my train DL and my test DL, and these are really very nice. We are almost there. We are about to build some neural networks using PyTorch. Okay. All right. So now I'm just going to print one of these just to show you these become essentially torch objects. So train DL, you can see it is now just a torch object. It's been wrapped around some code, but it's, it provides all the functionality that you need. So once we start doing the training, you will see how it works. All right, so now let's go ahead. And if you look over here, we are ready to start building our neural network architectures. All right, so we did the perceptron, and the perceptron had the most basic neural network architecture. It is, in fact, the original idea, right? We've looked at Hopfield networks. They're essentially kind of the same thing. Dot architecture was what? The dot product, right? It was the weights times the axis plus the bias. That was it. That was your architecture. Now we are going to build on top of that idea to start building, ever more complex neural networks. Okay. So I have here neural network architectures, and I have essentially here two neural networks. So I'm actually jumping ahead from the perceptron to the multi-layer perceptron, and I'm skipping like linear regression and logistic regression. We will come back to that. But right now, my point is just to show you really quickly how to get started. So today you're building your first deep neural network. You should be excited, right? All right, so how do you do this? Well, let's go ahead. You're going to want to use object-oriented programming. That's the best approach as these things become very modular really quickly, and then it starts to really pay off. All right, so you just kind of have to get used to this format. There's two approaches to building a neural network. Currently, I'm only showing you the first one. There's a second one using something called NN.sequential. I essentially like to use NN sequential when I do things like neural nets, which are more complex. But here, this is the simplest thing, so we just use this approach, which is very intuitive, I think. All right, so this is a multi-layer perceptron, okay? So essentially in the perceptron, we had one input layer and an output layer, and that's it, right? We would give it, some values. It would perform a dot product and give us a result. This one is going to be different because it's got an input layer, what is called a hidden layer, and an output layer. So going back to your reading notes, right? So you guys have some reading notes. All right, so the architecture for a multi-layer perceptron should be, you should read through all this, right? Read through all this material. But the architecture for a multi-layer perceptron should be, See, this is kind of like the perceptron, an input layer and an output layer. And a multi-layer perceptron is like that. An input layer, an output layer, but if you look in between now, you have a layer of neurons. And it's basically like it's a stepping stone, right? So now instead of having connections directly from here to here, you have connections into something in between. So before, what were we doing? We would take these values and perform a dot product between these and the weights to arrive at these. Now we perform two dot products, right? So a dot product between this one and the weights to arrive at here. And then this becomes another step where we take these values times these weights, perform a dot product to obtain this. Do you get that? That's essentially all that's happening there.
Just like that product once you reach the hidden layer, so it's just repeating what it did in the between the input layer. Okay.
Exactly like that. So before we would take this X times W and got the value, correct? Now we do exactly the same thing. This times the weights, get this, and now this becomes the input to the next thing. So this becomes, so before it was, so here it's X times W, and initially it was X times W equal Y, right? Now it is X times W equal H1. We just call this hidden layer 1. And then what do? Hidden layer 1 times W2 time, H1. Let me be consistent with the notation. So I'll do this again. X dot product W1 equal H1. And then H1 dot product W2 equal Y. And that's essentially what we do. Does that make sense, guys? Any questions on that? Nope. All right. Yeah, so that's what we're doing. That's the magic of neural networks. You just start doing more. And so now maybe in your mind, it's like, oh, wow, look at all these dot products. Now imagine if we have hundreds of hidden layers and thousands of neurons, right? That's a lot of these dot product operations. And that's where the CPU starts to slow down. And that's why we need a GPU, because GPUs are essentially processors that just do dot products, right? So that's the thing. All right. But anyway, so that's the multi-layer perceptron. So this part here, it's essential that you understand what's going on here, right? Because this is how you're going to build all your neural networks. So this is critical. This is called architecture. You're the architect of these, architectures. So you essentially do a class such as MLPNet, okay? This, most of these, although they can have more functions, the approach is to have one function like this, which is to init the class. This is the constructor. And then you have a second function that you called forward. Okay, so two functions in here. It knows how to use these because if you notice over here, every time you create a class, it's going to inherit NN.module. So if you remember from your object-oriented programming classes, you must have learned something called a class inheritance, right? So that's what this is. All right, so you inherit the properties of NN module for this class, okay? Then in the constructor, you start defining the properties. So for instance, this constructor is, underscore, underscore, init, underscore, underscore. So it's two underscores. Remember that Python classes have this word self. You do this super init to initialize the inherited class. And then after that, you just start specifying the architecture that you want to define. So in this case, we have to kind of learn how this works. There's going to be we're going to define the layers, and then we're going to define what we do to the layers, right? So there's these things called activation functions, but you already know what an activation function is, right? What's the one activation function that you're familiar with currently? The perceptron step function, right? So what would happen there? X dot product W plus B equal Y, and then that Y would go into the activation function to produce the final result, right? Same thing. The only thing is that activation function can be other functions, not just that simple 0 or 1. We have other functions like sigmoid, relu, tanh, gelu, etc., just inventions that are made, but it's the exact same idea. All right, so we're going to have here, we're going to learn how to create our architecture. Okay. So I'm going to use this kind of for that. So this is the network. That's why it's called neural networks, right? This looks like a neural network. This does not look like a neural network, but by writing this code, we are in essence defining that architecture. So ignore this for now, but this is that standardization that I did manually before. It's just that if you're going to deploy this model, it makes sense to do the scaling inside this architecture instead of outside. It just makes your life easier. But it's the same thing I did previously. So how do we do it? There is a specific construct called nn.linear in PyTorch. It is one of the most important things that you can think of. nn.linear, what you're seeing there is an abstraction of the dot product. You see what I'm saying? So instead of me here, so think about what I would need to do here. I would need to create an X, have an X, create a W, create a bias, right? That's 3 lines of code right there. Then take X dot product W plus B, that's a 4th line of code, right? And then that becomes the output. So 4 lines of code to perform that dot product operation. Now imagine that I'm doing a neural network with 100 layers. So then I would have to do that 4 times for each layer. That's 400 lines of code. Do you see that? So instead of directly doing the dot product here, PyTorch has invented this thing called nn.linear. nn.linear is doing the dot product inside, but you only do 1 line of code instead of 4. Do you see that? In a future example, I will break nn.linear more specifically into the details, but for now, that I'm saying, trust me that this is the dot product operation. Does this make sense? All right. So I define nn linear. Why 4 here? I have to specify these values correctly, especially the inputs and the outputs. So which data set are we looking at right now? We're looking at Iris, right? What's the input of Iris? What's the size of each input? It's 4, right? Because it's the vectors, F1, F2, F3, F4. So vectors of 4. So the input is always this value here, the first nn layer. So if I was doing images that are 28 by 28 and I spaghettify them into 784, then this value would be what? The input to the network would be 784. Do you see that? If I have 12 features for the wine quality data, then this is going to be 12, okay? That's always the input of your network. The last layer, which in this case is this one here, this value is always what? It's always the output vector of your model. All right, so in this case, we are predicting 3 classes, Setosa, Virginica, Versicolor. So this is going to be 3. Does this make sense, guys? So the last value depends on the number in a classification problem, depends on the number of classes. The first value depends on the number of features. What you do in between is up to you. Yeah. This 3 here. So think of Iris, right? Iris has 4 features, and then you predict 3 classes.
So it's label count.
It's label count, yes.
Okay.
Very good, very good. For a classification problem. So 3 is, yeah, label count, I like that, and this is the number of features. These 3 and this 3 I have not defined, but from layer to layer, they need to match. They are the architecture of your neural network, and you decide what it is. It's entirely up to you. Do you see that? So for instance, let's take a look at this graph, right? This graph, does it have 4 inputs? F1, F2, F3, F4 for Iris, correct? All right. How many classes does Iris have? 3. Setosa, Virginica, versicolor. Great. It's got one hidden layer. How many neurons are in this hidden layer? 4. Okay. So if I wanted to specifically code this architecture, I would go to my code and I would change this value that says 3 to 4. The key thing is these two values need to match because it's saying, you know, you have to think of it, it's going from, it's like this. It's saying it's going from 4 to 4 and then from 4 to 3. You see that? So you have to be consistent in that. If you add more layers, it's fine, but just make sure that the ending layer of one thing is the ending value of one layer is the beginning value of the next layer. Got it, guys? And just keep in mind, as I said, we're doing the dot products there. Any questions? That's it. That's how you do an architecture. And then in the second example, we will learn how to do a deeper architecture. I believe we can do this one. You see, this one has 4 inputs, 3 outputs, right? So this is not deep networks, deep neural networks. You in fact did Weka, right? The Weka program, and you did MLP, multi-layer perceptron. I've been using Weka since like 2007, before deep learning, before the deep learning revolution. And it was essentially, I was doing MLP, this architecture. You guys even tried this probably in your homework with a lot of data, and it took a very long time to train. Now, with Torch, we can build a network like this. Notice what's different about it. It has one more layer. And this term, deep learning, was coined by Geoffrey Hinton, who is the godfather of AI. He invented stochastic gradient descent, which is, if you remember, in the Hopfield network in perceptron, we talked about what Widrow did, right, with calculus and all that, how to calculate if we would increase or decrease, right, the value of the weights. Geoffrey Hinton solved that problem for deep networks and coined the term deep learning. But essentially, it's just adding a layer. So how does it work? You take this set X times, so let's say X times W1 equals H1. H1 times W2 equals what? H2, right? And then H2 times W3? Y. That's a deep neural network. See how it's the same idea of the perceptron, just a little bit more involved. The math was always there since the perceptron. Widrow figured out the calculus part of gradient descent, but implement an algorithm that would work in that structure was created by Geoffrey Hinton. All right. So that's what wasn't there back then. Also, the computing power was not there. All right. So we're gonna do this network too, but just showing you. So we're kind of sticking to this one right now, and let's just kind of finish going through all the details, right? So that's why the perceptron is so crucial, because it's so simple, but yet it gives you so many of the ideas already. So now I've created, and I haven't linked anything. So everything is just like defined. I've defined this and that and that. In forward, I am going to link them in a specific way. But here you can see I grow. So I'm going to switch this back to 3, or actually I can leave it here. So I'm defining linear 1, linear 4 to 4, right? Now in the perceptron, after that step, we had an activation. That step function that would give you 0 to 1. Here we do the same thing, but instead of that activation, we're going to use an activation called sigmoid, nn.sigmoid. This one, instead of being an if statement, right, that just looks at the value and says 1 or 0, This is a function that transforms the data to be within the range of 0 to 1. Do you guys understand that? So if your values are, let's say, from 1 to 75,000 or whatever, those values are now going to be mapped to be from 0 to 1. That's what sigmoid does. If you use 10H, then they're going to be from -1 to +1. If you use ReLU, if all the values are negative, they're going to be 0. And if they're positive, they're just going to be that value. So essentially, they're just transforming the data. And you should use an activation function on every layer, and you can play with those. Notice that then we define linear 2. This is going to be the dot product between the hidden layer and the final layer. So that's why it's 4, 3. The last layer has something called softmax. And softmax is really nice. Read the documentation that I provided because everything is explained there in extreme detail. But essentially what softmax is doing is the following. Let's take a look at these three outputs, right? So these three outputs, each of those neurons represents one class. So this is the neuron for setosa. This is the neuron for virginica. This is the neuron for versicolor. But because in a neural network, we don't use strings, we call them by numbers, so 0, 1, and 2, right? All right. So what this neural network is predicting is actually a type of a regression value, right? It's predicting, given the x's, it's going to say that this is 0.70, this is 0.5, this is 0.6. Essentially, it's going to produce a value between 0 and 1 for each neuron. And you can, to get a better understanding of this and intuition, think of that value as meaning the likelihood or probability that this input belongs to this class. Do you see what I'm saying? So for instance, if this produces a value 0.70, how can you interpret that? You could say there's a 0.70 out of 1 probability that this is setosa. Do you see that? Then you look at this one, and this one says 0.80. So what does that mean? It means that this has a 0.80 probability that it belongs to virginica. And then maybe this one has 0.10, and that means that it has a probability of 0.10 that it belongs to versicolor. You see that? So then what's the simplest thing? Just pick the highest value, and that's your class. So if this is 0.6, this is 0.8, and this is 0.1, which one do you select as your class? 0.6, 0.8, 0.1. The middle one, right? 0.8. That's it. That's how it works. Do you guys understand? Yeah. So the neural network needs to learn how to predict those values. So we're going to see how that works. What softmax does is it's going to further force the model to produce those probabilities, but they should add up to 1. So instead of saying 0.6, 0.8, 0.1, if you add those, so 0.6 and 0.8, that's 0.14, and plus 0.10, that's 0.15. It does not add up to 1. So you further force it to add up to 1 by using the softmax function. So the values would be transformed to something like 0.3, 0.6, 0.10. Now they do add up. And that's essentially what is happening there. We're going to drill down into this a lot more, but all of this, as I said, is explained in this document, which again, make sure you read. Okay? Any questions so far? All right, so we're building this neural network. We've defined the linear activations for each hidden layer, and then the function for the last layer, okay? All right, now, MLPNet, I have my next function, forward, and this is where I'm actually going to put together all the layers, right? So the forward function takes in x here, right? This is going to be my iris input, and it's going to go through the network layer by layer. So if you notice over here, I take this X, and I'm going to plug it here into linear 1. What is linear 1? Well, let's look over here. Linear 1 is this one, which is this layer, which is 4 by 4. So essentially, I take vector of X, dot product with W1, and it produces H1. There's a plus bias going on in there, just like with the perceptron, but I'm kind of like ignoring that to keep it simple. Okay? Questions so far? So with that step, I got as far as H1 here. So when I do this linear 1x, this is H1. I just, by convention, you don't want to put in X1 and all that. It just, there's no point to it. But if you wanted to, you can. What happens next? You take the H1, which is this X, and you plug it into activation 1. This is like the activation function of the perceptron. So what is activation 1? It is this one. And what is it? It's a sigmoid function. It just transforms whatever that value is into the range between 0 and 1. This is essential for neural networks to work. All right, you need to have these activation functions. Okay? Got it? All right, next step then. So we are still, so we went from here to here. We're still here. That the outputs of this have just gone through the activation function. Right? We're at that stage. Next step. So that's this part over here. Then this is plugged into linear 2. What is linear 2? So we can look it up. So linear 2 is a dot product between that 4 and 3. So now we go to the graph. 4. So it's going to be these 4 dot product W2 to give you this one, which is the Y value, right? You're at the labels essentially over here. So that's this X here. But if you notice, there's still one more activation, which is to take this X, plug it in here, and run it through activation 2. What is activation 2? This one, which is defined as a softmax, nn.softmax. That's it. But, it's the same idea of the perceptron. That hasn't changed, really. You've just made the architecture deeper, longer, etc. And then, obviously, the learning rule of the perceptron does not apply here. You have a different learning loss objective called cross entropy, which is a big topic that we'll spend about a week on later. All right? So that's it. You get Y-pred. There you go. Y-pred is then this vector of 3 here. And the forward function just returns Y-pred. You guys get that? So let's go ahead now. So that's it. You've just learned how to create your first neural network architecture, a multi-layer perceptron with PyTorch. Are there any questions before I move on? All right, no questions. So now let's take a look. So I'll skip the deep learning model for now, right? Instead, let's go with this multi-layer perceptron and let's define the training loop. If you remember, the perceptron had a training loop, right? So the perceptron had a training loop. And this one also has a training loop similar to it, but just it will not use the perceptron learning rule. It'll use other things now. Especially this is where PyTorch does the heavy lifting, right? Because it's going to implement Jeffrey Hinson's stochastic gradient descent algorithm. So let's go now. And I'm just going to copy the whole training loop. All right. So if we look at the training loop, it's just a function, right? I'm going to, before I describe this function, let's just add the code for the next section, given that a lot of those values are used in the training loop. So I usually refer to as the core functions for MLP, something like that. Sometimes I call it the main loop, but it's essentially where I instantiate everything and call the train loop and so on. All right, so we can do Markdown. I'm going to do run. I'm going to do this. All right, so if you notice here, first thing I'm going to do, let's delete this part. I'm going to instantiate my MLP.NET neural network, right? I'm going to instantiate this one, the class. That's all it is. I need to instantiate something called an optimization object. This is Jeffrey Hinton's magic, all right? Torch.optim.atom. For now, just treat it as a black box, but this is why he won a Nobel Prize. Okay, so this is not any trivial thing. This is literally a Nobel Prize right here. All right, so what's important about this is the algorithm that is going to train the model, which essentially means what? The weights are random. After training, the weights are the valuable information, just like it was with the perceptron when you moved it to your PyScript code. So what you need to do is you need to grab the model, and from the model, you use this called model.parameters. That extracts the weights and the biases and links them to this algorithm. So it's essentially telling Optim that it needs to train those parameters, the weights and the biases. You also provide the learning rate, which if you remember, it's by how much you add or subtract from the parameters, right? When you're doing the update. Same idea as the perceptron. That has not changed. You're going to also use something called a loss function, which is essentially that second equation that we were talking about. So there's the inference, and then there's the loss, the objective that you're trying to optimize. In this case, like minimizing the error. Do you remember that? So you're going to take the model predicts something, you have the real label, you compare them, and you minimize the error. So then here instead of using MSE, for classification, we use something called cross entropy. So I said, for now, don't worry about this. This is one of the most important discussions that we will have later on, how that works, but we just need to define it right now. And that's it. Once you have that, the training loop takes in opt, loss fn, the model, and the number of epochs, okay? So we're gonna go back to the model over here. Now, the training loop is a lot like the perceptron, if you notice. Let's break down to see what's happening here. So we're going to run training loop. Notice it's got two for loops. Do you see that? Why two for loops? The first for loop is, it just says, I want you to repeat this 4,000 times. This is the analogy that I was giving to you the other day, that if a little kid is running around and trips on something, right? After it trips maybe once or twice, it's going to learn not to trip on that, right? But the analogy here is that a neural network would need to trip on that 4,000 times in order to learn it, right? So that's kind of how it works. So you're giving the same amount of data to the model and epochs, so 4,000 times. Then after that, you have a second for loop. So each one of those epochs, what do? From train DL, our data loader, you just grab XB and YB. This is where now the data loader starts to pay off. So you say for XB, YB, and train data loader, you essentially grab a batch of data. And also, every epoch, the train DL will be shuffled also, and it does it by itself. All right? So you grab the data, and what do? What is XB and YB? They're tensors, right? What do they have? XB, let's say that my tensor size is 16, right? That means I give the model 16 samples at a time. So what is the shape of XB? 16, 4. What is the shape of YB then? You guys know this. 16 comma 1, because it's the labels. Do you guys understand? So you're giving it the labels and you're giving it the data, but in batches. All right, so then we give XB to the model because the model doesn't need the labels, right? It's supposed to predict the labels. So we give it XB and we get Y pred. So what is Y pred? The predicted labels. And then what do we do with those predicted labels? They're in Y pred, and you take YB, which is the real labels, and you calculate the loss calculation, which is essentially like measuring the error of the predictions. Does this make sense? So this, although it uses cross entropy, just think of MSC for now. And you'll see that cross entropy has some similarity. It's just a different way of calculating things, but it's essentially the same idea. You're trying to minimize an error. Or you haven't minimized it, but you calculate the error. Do you guys see that? Now, the key question is, all right, you've calculated this loss value. Now you need to minimize it. Do you guys see these 3 lines of code? These 3 lines of code will always be in your training function, and they do the magic. So it's going to take the data in loss, because remember, at the end of the day, what you're building is a computational graph with everything, right? All tensors and operations coming in, the predicted and the real, the difference between it, and that's loss. And then here you do this. So zero grad is kind of a thing that zeroes out an accumulator. And then you have loss dot backward and op step. What's happening here is that's that calculus part that we had discussed before. Loss backward does what? It calculates, it does the gradient calculation. Do you guys remember what that was? We talked about it, right? If you're at a point in the curve, it tells you if you should go left or right, go up or down in the curve. That's what backward does. So it essentially tells you if you're going to add or subtract from the parameters for each one of them. And then once you've calculated that, so imagine that all that calculus stuff is done just by one line of code in PyTorch for all the parameters, which could be billions of parameters. And then once you've done that, you perform the step. The step is just updating the weights. So the perceptron learning rule is this, but it's specific for your deep neural network. Make sense? All right. So that's the key thing. This will always be in your neural networks, okay? And think of it as the perceptron learning rule. And that's it. That's it. So we are ready to train our model, and then we would be ready to evaluate it. Okay, so let's go ahead and do that. So we should get something like this, basically. All right, so let's do that. So training function, load that into memory. And then now I'm going to instantiate everything. And there we go. Your first neural network training with PyTorch. So what do you want here? You want this loss function to go down. So if you look 1.09, 0.97, 0.71, 60, at some point it kind of starts to like plateau, but it went down a little to 0.55. You guys see that? Sometimes it can go up. This is not like, it depends on the data, the architecture, etc. But this is the process. That's it. This is your first neural network, a real multi-layer perceptron with PyTorch. So your homework will be similar to this, only I'll give you some other data set or something. Any questions? All right, so let's let it train. Once it finishes training, I'm going to evaluate performance, just like we did before. I think it's even the same function we've used before. And then we're going to build the architecture for a deep neural network. The point, though, that the great thing about it is you already did a multi-layer perceptron, so you already know how to do that by 70%. You're pretty close. All right. So I don't know how many epochs did I say for this. All right, so it's going to do 4,000 epochs. That's fine. Keep in mind, the deeper the network it is, the bigger the neurons, the slower it's going to be. So you can see how, look at how this is Iris, right? It's tiny, and yet it took a bit, right? And so obviously, as we start to get into bigger things, it's going to take longer. So things like Colab or Scholar will become very important. All right, so it finished here. You can see it got us down as 55. It kind of got stuck there. At that point, you have to start improving either the data or the architecture to get better results. Invent a better algorithm. All right, but this is where we are right now. So now let's evaluate the model. So the model is now trained. That means that the weights of that model are good ones. And we now evaluate performance. So what I'm going to do is I'm going to use, I believe you guys had seen this function before, correct? I think I did it with K and N. It's the same function. So I just give it the predicted values, the real values, and it's going to compare them essentially. And give me the precision recall F measure scores that we are familiar with from Weka and from other places. So now what I need to do is I need to run that test set, run that model on the test set, predict, compare those predictions to the real prediction, to the real values, and then measure how close they are. And that gives me an idea of performance. So let's go over here. All right. So if you notice, I'm going to do one thing here. You can see I'm doing with torch.nograd. What that means is that, whenever you use the network in some way, it trains by default. So when you're evaluating on the test set, you don't want to train with that data. So you just tell it something like with torch.nograd, and then essentially it's not going to update the weights for this piece of code here. So what do? We grab testDL, right, our data loader, and we say for x real, comma, y real in testDL. What are we doing? We're grabbing the data. What are the dimensions of this, of x real? What are the dimensions? 30 by 4. 30 samples, 4 features. What are the dimensions of y real then? 30 by 1, exactly, very good. So yeah, you always, in deep learning, at least where we are today, those dimensions are very helpful. Then you feed x real into the model over here, and it'll predict y pred. Do you see that? So x real feeds into model, and the model is trained, and now it's given you its predictions, y pred. And essentially what I'm going to do from y pred here is I'm going to grab the maximum. I'm going to use torch max to get the indices. You see that? Because it's giving me the vector essentially, but I need the highest value. So I'm picking it out. So that indices I assign to preds, and then I assign preds here, and I compare it to y real, and I calculate the performance. And that's it. So let's go ahead and do that. So what do you think? Since you guys know how to interpret this, are these good or bad results? Very good, right? So you have an accuracy of 0.97, precision of 0.97, recall 0.967, F1 measure 0.967, and you have the values on the diagonal. And how many errors do you have? you have one error. That's right. So yeah, that's it basically. So you've established, we've done the first multi-layer perceptron, we've evaluated it. We know it does really well. All right. And now we can do the next neural net. Okay. So if you notice, I'm going to do kind of the same thing. I'm going to instantiate the DL net. I'm going to do the training and measure the performance. And all I'm going to change is the architecture. Okay, so I'm going to, now you guys kind of know how to do this, but I'm going to define this new class. So I'm going to do control copy. All right, I'm going to do deep neural net or DL net. DL net. So it's going to be deep neural net. All right. So markdown. Gonna hit run. And we define our architecture. So if you notice, this can be a deep neural network of however many hidden layers. Now, keep in mind something like ResNet has 50 layers, right? Transformers, can have hundreds of layers. This one only has one additional layer to the multi-layer perceptron. All right, so but the approach is kind of the same. So we create a class DLNet. It's going to have class inheritance over here, so nn.module. So the same thing as before. We have our init function, super init. This initializes the inherited class, okay? And now we use a lot of the same objects, but we're going to have one additional hidden layer. So notice that before we had only linear 1 and linear 2. Now I have linear 1, linear 2, and linear 3, right? So which architecture am I going to build now? I'm going to build this architecture. Notice that the input has 4 features. The output has 3. And I'm going to build these 2 hidden layers to have 4. But I could have 8 here. I could have 300 here if I wanted to. It's entirely up to you, okay? As the architect. So let's look at the first one, right? So I'm going to do, remember, and these are the dot products, right? Dot product of X times W1 to produce the next layer. But instead of doing all that stuff manually, you have this construct called nn.linear, which streamlines a lot of the code. So I'm going to do nn linear from 4 to 15 here. So if I did this example that I have, then this layer would have 15 neurons, okay? If I want to keep it consistent to what this shows, then this value would be what? If I want it like the picture? 4. Now, if that's 4, what should this value be? Exactly. It's 4. It's 4 because it's like, it goes from 4 to 4. And now in the next one, you go from 4 to this one here. All right. Do you guys see that? So if I go to the next layer, well, now it's 4 from here to what? To this picture, that's also 4. So you can see how you can change those. And if that's 4, then this needs to be 4. Those need to match. So that now when you go over here, it's 4 to 3. So that this picture and the definition of this architecture are consistent. Okay? But we can have other architectures. You can define it how I had it. So 15. With the only condition that if this is 15, then this has to be 15. You see that? And then for whatever reason, I just want the next layer to be 9. So then just make sure. So when you guys do this in your competition or whatever, you can try however many architectures you want. You can do them however you want, okay? But there's no like science or theory here with this. It's very experimental, okay? It's kind of trial and error, but there are some, I guess, guidelines sometimes to follow. For instance, the idea of funneling things. So if you start big, you funnel it into something smaller. So that's especially important if you have images. But because Iris is already very tiny, the vectors are of size 4, then, funneling is not such a critical thing. Guys, do you understand this part? Because this is your first deep neural network. It's like the essence of the class. Do you have a question? Yeah, go ahead.
So you always have to start with the inputs and the output, like the label, right?
Exactly.
And then numbers.
It's up to you. Just be consistent. But yeah, you're right. You always start with the inputs because that's the data. That's literally the thing that you're showing the model. And the output is, your classes or regression or whatever it is that you're predicting. Yeah.
So in between layers, it's possible for the amount of labels you have to shrink because we start with think
of everything as neurons, and the only thing that is the output are usually the labels.
Okay, so I was thinking of it completely wrong. I was thinking that somehow those 4 neurons in between could also correspond to labels. Those are just like you have features.
They are transformed inputs. That's what they are. So if you think about it, we'll do an example of this. This is a vector space, and this is a transformed vector space. And then this one is a transformed vector space. It's just the same data. Every sample in here will be still that sample, but it'll look different. The model is changing it a little bit. What it's doing is it's getting rid of unnecessary things and highlighting the things that it thinks are important. Do you see that? So if you're trying to determine cars, right? So it's going to take pictures of cars here. By the time it gets to here, it's gotten rid of backgrounds, it's gotten rid of things, and it's just focusing on things. So it's just transforming the original data so that it only keeps the thing that's the most valuable to tell the difference.
So it's like transformed features.
Yes. Yeah, I would describe them as that exactly.
And the only labels aren't changing or shrinking or anything like that. The labels are just the output over there. So nothing changes with that matters.
The labels are, at the end of the day, it's trying to take the inputs and tell you which one of those labels is more likely to be the correct one.
Okay. All right. I see where I was going wrong.
Yeah. Like if you think of it this way, right? So here's a way of thinking about the way that you're asking. You give it this input, and then immediately you have to say if it's one of these 3. But if you have these layers in between, what do? You can take this data and kind of modify it to highlight certain things and maybe drop some things that are confusing. So then that's a better way of looking at the sample. And then you do that again. So it's you're just having more room to kind of decide what class they belong to.
And is it doing that via the use of weights?
Yeah. Okay. All these lines are weights. So remember, an X vector dot product weights produces an H1 vector, and then this H1 vector dot product, these weights produces an H2 vector, and this H2 vector dot product weights 3 produces the final Y vector. And that is supposed to mimic the thing that you're comparing to. So remember that this is the predicted vector of 3. This predicted vector of 3 is compared to a real vector of 3. See that?
I think so.
Yeah, and we'll this is a good example. We'll take a look at it in the future, but yeah, this is the procedure. So now let's take a look at So we have our deep neural network architecture. So from 4 to 15, 15 to 9, 9 to 3. Notice that still activation functions, only I have called these activation functions now ReLU. So you've seen the step function from the perceptron. Sigmoid is an activation. ReLU is an activation. There's softmax. And there's other activations, TANH, GELU, and so on, right? So these are all like the activation, just take the output, modify it a little bit. Yeah, go ahead, please. As far as the activation, ReLU is probably the better one. There are other ones like GELU that I see being used that are newer, but ReLU essentially, there's something called leaky ReLU, and that one's a little bit better. Sometimes you just have to play with them. All right, so now let's do the inference, right? So in the inference, we take the X data, okay? So that is essentially this vector of 4 goes in, right? So this X goes into linear 1. So it's going to be 4, so 415, right? So when it comes out here, this is now vectors of 15, not vectors of 4. Do you guys understand that? So I've literally, that's why I keep saying I transformed it from one vector space to another vector space. Because before the vector space was of size 4 dimensions for each point. Now those points are in a vector space of size 15. But that somehow might give you insights into how to understand this. So linear 1, so this X is now here, right? And it's 15 neurons. So then this X goes into activation 1, which is a ReLU. So that modifies the data and produces this X. This X then, this dropout, let's ignore it for now. We'll come back to that later. Just ignore it. So this X goes into linear 2. Okay. What is linear 2? Here, which is 15 times these weights to produce this vector, which are now of size 9. You see that? Every sample is now a vector of size 9. It's been transformed further. So 4, 15, 9. So linear 2, it produces this X. This X goes into activation 2. ReLU produces this X. Ignore the dropout, and now it goes into the final linear 3, which linear 3 is from 9 to 3. So here we arrive at that point. That's this one over here, right? And then this vector plugs into the softmax function, okay? Which is going to be activation 3 over here, Y-pred. You guys see that? All right. So in another example, we'll look at plugging values for softmax, but it'll make sense. Like, you know, it's just a function, and you'll see that makes a lot of sense why you want to do that. It just helps the model. That produces our Y-pred, and that's the architecture. Are there any questions, guys? This builds your first deep learning model. So now let's go ahead and run that code. So that code is now in memory. So now we're going to instantiate this one. Very similar. That's the beauty of this approach, right? That you can easily just change one model with another. So notice that now, instead of MLPNet, I'm using DLNet, okay? And the same opt, I map the model parameters here. To opt them, I use cross entropy, which we'll discuss in another class, and I'm going to perform the training. So let's go ahead and run it. And there it goes. Notice that it's a little bit slower now because this is a deeper neural network. So it goes 1.08, 60, 55, 55, and this is going to be 4,000 epochs again. And then finally, we're just going to measure the performance. Don't expect it to be better. I mean, the other one was already good, right? But obviously, the more difficult the data, the better results. Iris is, one of the easiest data sets. So you can see it's training. I didn't normalize the data. So, oh, yeah, I haven't. So, or did I? I don't think I did. So that maybe could improve results. That dropout could have, there's a lot of things we can do beyond that, but this is just the most basic stuff. And I don't want to overcomplicate. Any questions? That's it. I mean, all I'm going to do now is I'm going to run this one and then print the results. And that's your first example. That completes this Jupyter. I'll load it on the 2025 folder. And then on Wednesday, we'll probably do the wine quality. So that one is not Iris. It's a different, a harder problem. Any questions? Yeah.
But when it comes to next one,
Yeah.
I think it might be another web implementation.
No, this one will just be like this.
Entirely training. Actual training and testing.
Yeah, it'll be like this one with another data set. So it might be a challenging data set. Might be the fraud data set. I'm not sure. I haven't decided yet. Or it could be images. And then there will be one homework though, where you do web, but it's going to be with Onyx.
That like a different sort of
Instead of PyScript, it's Onyx. So you take this model and you export the model and then you load it to a website. Still in GitHub and still in Pages.
Does it like kind of function the same way as PyScript?
It's
like,
no, this one is more JavaScript.
Oh.
But because you're not coding the dot product from scratch, you're going to have a model. So you really need to like have a file that contains the model and then you just read it.
Oh, so it's going to be linked to its own separate file.
Yeah, the model is going to be in a file. And then from JavaScript, you import that file and that's the model. And you just have to give it inputs and it gives output.
Like easy with PyScript then.
The
PyScript had to like recode the entire model.
Yeah. So again, both of them, you don't have to do the training on the web. You just do it on Amazon. But yeah, there will be definitely the only homework I have planned so far is this one, the PyTorch homework. So probably by this Wednesday, I can give you something.
Okay.
I just haven't decided on the data set. I'm thinking images. But... All right. So I think it finished. That's still 55 at the loss function. So you would want this to be lower. I'm going to hit run. And you can see it's actually not better. It was worse. You see that? 0.93. Just because it's deep learning, it doesn't mean that it's going to be better. However, you may get much better results on harder data sets. You see that as so it is. I would also, in my example, I think I had 96. So this is why you don't just want to run it once, right? But you want to run it multiple times. And then this might be on the low end of the performance. Any questions? All right, that's it for your very first example. So you've implemented a deep learning neural network, all right, with Iris data set. On Wednesday, as I said, we're going to repeat this exact same exercise with the wine quality data set. All right, guys, so we can stop here for today, and I will see you on Wednesday.